All right, so let's get started. So we'll continue on the second lecture of collective neutrino oscillations. And in the last lecture, I gave you a somewhat lengthy introduction and overview of some of the numerical calculations we have done and other groups have done. And today, I will focus on how we can use some simple estimates, tools, and models to understand those calculations. And after all, we are physicists or astrophysicists. We are not just simply computers. So we need to understand them. And then using those models, and we can build up physical insights. And that will direct our further, more complicated numerical calculations. And I had a discussion with Shashank the other day, and he is writing the code for a new model. And somehow he found out in one of the cases there were neutrino oscillations, but in the other case there were no neutrino oscillations. And I told him from the simple model I had, you should expect oscillations in both cases. So he went back and then found out there was a bug in the code. And that bug may not be easy to find, as if you have really write a program, you know it's how hard to get the code right. There are all kinds of bugs. The easiest one, maybe the most difficult one to find out, is a typo. So we will see. All right, so just kind of repeat a short introduction of neutrino in supernovae. And so we know the supernova is quite energetic. It releases about 10 to 53 ergs of energy in total, and 99% of them come out in neutrinos. There are 10 to 58 neutrinos released in 10 seconds. Compared to the Avogadro number 10 to 23, this is a really, really big number. And we have neutrino in all species, electron, mu, and tau flavor neutrinos, and they're antineutrinos, and with energy of order 10 MeV or so. And obviously, neutrino will dominate energetics, and Tony showed you how that can revive the shock and explode the star, although with help of convection and Sassi modes. And then neutrinos also influence nuclear synthesis, as Jan has told you. Basically, we're interested in, or for most application, physical applications in supernovae, we are interested in electron flavored neutrinos and antineutrinos because they deposit energies into the matter. And also, they flip a neutron to proton and vice versa. So that determines the neutron to proton ratio in the neutrino-driven wind in supernova. So that will influence nuclear synthesis and what kind of unprocessed elements you can get in the end. And also, the neutrinos, if we can detect them, that can also tell us about what's on top of the neutron star. Maybe we will, that will kind of indirect probe into the hot dense matter within the neutron star. But even that, we cannot get from the photons, because photons won't decouple very, very, very far away from the center of the neutron star. But neutrinos can probe right down to here. But doing neutrinos, we know neutrinos can oscillate. That's actually is an established experimental fact. And if you put that fact into supernova neutrinos, you find out it's a very difficult problem to solve. So here is a shorter equation you have learned in undergrad quantum mechanics. And now the Hamiltonian have three parts. The first part give you the vacuum oscillations, and the second part is the matter effect I told you before. Basically, that's a refractive index of neutrinos in matter. And then the third part is due to neutrinos have to pass through a very dense medium, 10 to 58 neutrinos in 10 seconds. So there's a very dense neutrino medium, and that will also change refractive index of neutrinos. So you put all those terms in and say this is your neutron star emitting neutrinos, and so this is easy to solve if there's no neutrino-neutrino forward scattering. But now with the neutrino-neutrino forward scattering, say you have two neutrinos, nu k and nu p, they intersect with each other. Then after the intersection, their flavor history somehow become coupled because they depend on the history of each other before the intersection point. And then this nu k can intersect with nu q, and so they become correlated. And even more interesting is nu p and nu q, even though those two neutrino beams, they never intersect with each other, but you see in the end their flavor history are correlated. So that's a very interesting fact. And as I mentioned in the last lecture, if you think along this line, neutrinos emitted from every point on the neutrino sphere with all different momentum energies, different directions, with different flavors, their flavor evolution can all become coupled. And this is a very daunting numerical problem. So we are talking about the 3 plus 3D. And the first 3D refers to the spatial. So the wave function, the flavor wave function of the neutrino depend on the radius, how far you are away from the neutron star, depend on the emission points on the surface of the neutrino sphere. There are two angles. And then depend on the neutrino energy or the absolute value of momentum, and also depends on the direction of the momentum. So that's a 3 plus 3D. And here we actually assume neutrinos are completely only depend in experience coherent forward scattering outside the neutrino sphere. And in the next week, George and his student will talk about what if you take into account the neutrino scattering with other particles that will change direction or can be absorbed. So that's an even more daunting task. So this problem is too hard to solve. So let's say, what if there's the neutrino sphere and the supernova has axis symmetry along the z-axis, and that will reduce the spatial dimension down to 2, but that's still hard. And then what about down to 1? So assume the supernova is spherically symmetric, and that's a 1 plus 3D problem. And that problem actually has been done recently by Mirisi et al. But the problem here is, if you assume the neutrinos can evolve independently in the phi angle, which means if you choose any radial direction, the phi angle is around, azimuthal angle around it. So if the neutrinos behave differently or evolve differently along different phi directions, then that will actually break the spherical symmetry of the supernova. So you will automatically break this 1D. So we think that model is not self-consistent. So mostly for the last 8 years, what we have solved is called this the neutrino Bob model, or the multi-angle calculation. This is a 1 plus 2D, and depends on the radius, and also depends on the neutrino energy and the propagation direction, the zenith emission angle. And also I mentioned that there's a single angle approximation, which is we just make a further assumption that the neutrino evolution is independent of neutrino trajectories. And also that model is equivalent to an expanding homogeneous neutrino gas. So here is another simulation I didn't show you the other time. In the last lecture, I showed you 3 that probably all look the same to you, and this is probably also look very similar, but in our eyes, they are quite different. And let's see if we can tell the difference. So again, the upper two panels are the neutrino survival probability. The red color means if you have an electron flavor neutrino on the neutrino sphere, red color means currently is still 100% electron neutrino. And the blue color means now it becomes a mu or tau flavor neutrino. And the left panels are for neutrinos, right panels are for anti-neutrinos. The horizontal axis are the neutrino energies from 0 to 60 MeVs for both upper and the lower panels. And the vertical axis for the upper panels is a cosine of the neutrino emission angle theta r, as I mentioned in that 1 plus 2D model or the neutrino Bob model. And then here are the energy spectra are showed in the bottom panels. The dashed curves are the energy spectra on the neutrino sphere, the red color for electron flavor neutrino, and the blue color for the nu mu nu taus. This is a 3-flavor calculation. And the solid line shows the spectra of nu E and anti-nu E at the current radius, which is given by this blue bar in the bottom. So this is the radius from the center of the supernova in units of kilometers. Right now it's about 100-something kilometers. All right. So what I am showing you is essentially similar to a neutrino tomography. So each time frame of the movie shows the neutrino energy spectra and the flavor content as I move away from the supernova with a fixed snapshot, fixed instant. Let's see if you can see anything different from the previous calculations. A major difference actually show up here. Alex Freeland was very fond of that interesting wedges. They are very different from previous calculations. It kind of shows that there probably is some kind of a different flavor instability going on. And I will come back to that wedges later. Yeah, also this band become more narrow, and again you have a swap, the spectral swap between nu E and the nu X flavor, but this is at lower energy than in the previous calculation. And also here you see the final nu E spectra is not completely nu E or not completely nu mu or nu tau, so it's a different. Anyway, so the conclusion from the last lecture was just as Tony said, yes, you can make scientific discoveries through numerical calculations. But I also give you a warning, as Jan tried to emphasize, you got to know what's going on in your numerical calculations. So we got the big boxes upstairs, but are you sure what's going on inside? So as a physicist, we need to understand our calculations. So as a first step, let's just see what we can get out of it without actually doing real calculations. Just do some estimates. So let's just stare at the Hamiltonian. And the Schrodinger equation, the Hamiltonian have 3 parts. The first one gives you a vacuum oscillation, which is a mass squared matrix of the neutrino divided by twice neutrino energy. The second part gives you the refractive index of a neutrino in the matter, proportional to the electron number density. And the third one gives you neutrino-neutrino forward scattering. Is proportional to the flavor density matrix of the neutrino, background neutrino, and integrate over. And also there's a geometric factor, which is also important. So let's just stare on it for a second. Now what you can say. So there are those three terms give you 3 energy scales, basically. The first one give you this energy scale, mass squared difference over twice neutrino energy. Although this matrix is a mass squared matrix, but really what's important is the phase difference of neutrinos in different states. So what's important is not the mass squared itself, but the difference of those mass squared. So that determines this energy scale, mass squared difference, say m2 squared minus m1 squared, then divided by the neutrino energy. So that's the important energy scale that actually tells you how the oscillation frequency in the vacuum. The second energy scale is given by this term. That's easy, just the Fermi coupling constant that determines the strength of the weak interaction and times the electron number density. That tells you how large is this refractive index. And then the third term is just a Fermi coupling constant times the neutrino number density that is similar to the matter effect, tells you how strong is the refractive index of neutrino in the neutrino medium. All right, so let's just look at MSW first. We know that for MSW effect to happen, it happens around the MSW resonance. This has happened by comparing two energy scales, the vacuum energy scale mass square difference over neutrino energy, and the matter energy scale, G Fermi times electron number density. When those two terms are comparable, we know there's an MSW resonance. And we can look at, so there are three masses for neutrinos. So there are two independent mass square differences. One of them is called the solar mass square differences, which is measured through solar neutrino experiment. If you put a 10 MeV neutrinos down here and use the solar mass square difference, you get this energy scale. So we, as a nuclear physicist or particle physicist, you take h bar equals c equals 1. So the energy is the same as 1 over length. And so I measure the energy by the 1 over, in the unit of 1 over kilometer. So that's convenient in supernova. So for solar mass square difference and 10 MeV neutrino, the vacuum energy scale is about 1 over 50 kilometers. And that if you put the atmospheric mass square difference in, that's about 1 over 2 kilometers. And what about the matter energy scale? That's huge. The distance scale is very small, but 1 over the distance means a very large energy scale. And you know in the vacuum, lambda matter is 0. So that means from the center of the supernova to outside, you will definitely go through both energy scales, and you will have two MSW resonances, one at here, the other at here. So that means you got the 3 flavor MSW. And here we have, for MSW, adiabatic MSW, we assume the matter density changes very slowly, but the changing rate of the matter density or the matter energy scale actually give you another scale. So if that scale, or the changing rate of the matter density is too large, is much larger, is larger than the vacuum energy scale, then you got a non-adiabatic MSW flavor evolution. And that's how Schroeder and George, they come up with this neat idea. When you can actually track the propagation of the shock wave from the supernova neutrino signals. And also, that's also another idea by George and also Freeland, Alex Freeland. They found out that if you have a turbulence inside the supernova and then the matter go through it, that turbulence will also imprint on the neutrino energy spectra. And in the end, you could have a flavor depolarization, which means the nu E, nu mu, nu tau, they all have the same energy spectra. That's called the flavor depolarization. In terms of the flavor density matrix, what you obtain in the end is a proportional to a diagonal, to an identity matrix 1, 1, 1. So now let's come back to collective neutrino oscillations. So we have compared the vacuum energy term and the matter term that tell us about the MSW effect. Now we want to compare the vacuum term, vacuum energy scale, to the neutrino energy scale. And that will tell us about the collective neutrino oscillations. And first of all, the vacuum term energy scale actually depends on neutrino energy's mass square difference over twice neutrino energy. And what's really important is not the vacuum energy scale itself, but how it is spread out. Because if all the neutrinos, they all have the same energy, then they will oscillate completely in phase. Right? So that's a trivial collective oscillation. This is not something we are talking about. What we are talking about is neutrinos with different energies and also neutrinos and antineutrinos they will oscillate in phase. That's a different idea. So that means what's important really is the spread of this vacuum energy scale. So what do we call it? Is dispersion in energies, vacuum dispersion energies. So the basic idea is if you compare those terms, we would expect the dispersion, the vacuum dispersion energies, if it's smaller than the neutrino energy scale, then you will have collective neutrino oscillations. So that's a naive idea, but now I put this geometric factor in. And why is that? The reason is, if you look at the neutrino coming out of the neutrino sphere, they intersect with this angle. And you recall in the neutrino Hamiltonian, there's a geometric factor 1 minus p dot p hat, p dot p prime in there. And you need to average over that factor. So this is given by this factor, and the theta is the angle between the two neutrino beams. Why is that important? If you look at this factor far away from the neutrino sphere, the first one, the neutrino energy scale itself, or the neutrino number density, go down like 1 over r squared. But that geometric factor also go down as 1 over r squared. So what's really happened for this neutrino Hamiltonian is actually go down like 1 over r to the 4th power. So that makes a great difference. So that's why we say if you want to have collective oscillations, you got to have this neutrino energy scale times that geometric factor larger or comparable to the dispersion in vacuum oscillation energy. All right. But that's not the complete story. In fact, we have known for quite a while that if that dispersion in energy, the vacuum energy scale, its dispersion in energy is much smaller than the neutrino energy scale times that geometric factor, actually nothing happens. The reason is that, as I mentioned earlier, in that regime, all the neutrinos, through their interactions, they are actually locked in. They are locked as one single neutrino behave just like a single neutrino with some characteristic energy. So if that neutrino does not go through MSW resonance, you will see no collective oscillations. So that's the idea behind it. So what's really important is you want to have that dispersion in vacuum energy scale be comparable to the neutrino energy scale. So that is where we expect neutrino oscillation to happen. Now what about the matter terms? So we have compared the energy scale of vacuum with matter. We have compared the energy scale of vacuum with the neutrino. And now we compare the energy scale of matter with neutrino. There are only 3 terms in the Hamiltonian. So naively, you would say if the matter energy scale is larger or comparable to the neutrino energy scale times that geometric factor, neutrino oscillations will be suppressed, can be suppressed by matter, because the matter has nothing to do with the neutrino, will not help with neutrino oscillations. But that's actually not true. So if you look at the uniform and homogeneous isotropic neutrino gas, and if you have a uniform matter distribution, so those are the keywords. If those conditions are satisfied, then collective oscillation will still happen even if you have a very large matter density. And why is that? It's kind of similar to the idea how you understand Einstein can find an inertial frame at any point, even though the space-time is curved. So if you are in an elevator, the space is small enough, and then it's moved with the same speed, then you will not feel gravity inside. The idea here is similar. If you have the matter density is uniform, and then that somehow can be get rid of. And I will talk more about that later. But that's a basic idea. If you have a uniform condition and also the neutrino gas is homogeneous and isotropic, the matter density actually does not matter that much. And we actually have seen that in our calculations. For example, in this plot, the horizontal axis is the radius of the in kilometers, and the vertical axis tells you how different is the current neutrino energy spectra from the initial ones on the neutrino sphere, and that's in the logarithmic scale. So the black curve is our kind of standard calculation, and you see some slow growth. That's really, I'm not sure that's really neutrino oscillation. That's probably due to the MSW. And then this is where the collective oscillation begins. You see a fast exponential growth. And that we'll talk more about that fast exponential growth later. And then when it reaches about order 1, it will keep in there. So that's the maximum you can get. But if I dial down the neutrino matter density by a factor of 5 or dial up by a factor of 5, where collective oscillation begins doesn't really change much. So collective oscillations does not fill matter density. That's interesting. And we'll talk more about that later. But there is a small effect. So with the higher matter density, that kind of push the collective oscillation back a little bit in radius. And why is that? That's because neutrinos are coming from a source, from a neutrino bulb or neutrino sphere. It's not a homogeneous neutrino gas. It's not homogeneous and isotropic. So if we have collective neutrino oscillations and we have a spherical symmetry in the supernova environment, then the wavefront of collective oscillations will be spheres, co-centered with the neutrino sphere. And if we look at those two neutrino beams, when they pass through those two wavefronts, they actually propagate throughout the different distances, right? So what's important for matter is not the matter density itself, it's not the energy scale of the matter itself, but rather some kind of dispersion because of the path length. And so I would denote it as a delta lambda matter. So what's important is to compare that energy scale with the neutrino energy scale times that geometric factor. When those two terms are comparable, you will have suppression of collective oscillations because the length scale, because the dispersion in matter is so large, and the neutrinos propagating in different trajectories will build up different phases, and then they will not be collective anymore. So that's the basic idea behind it. But you see this dispersion in matter scale, the matter density usually come down either exponentially close to the neutron star or go down like a 1 to the 1 over r cubed or 1 over r squared. So that really is go down very quickly, and that geometric factor in the path length give you another 1 over r squared. So in the end, the matter suppression should not happen except in some cases like very close to the neutron star or in the very early epoch and in the ion core collapse supernovae. All right, so this matter suppression mechanism is actually a kind of a multi-angle suppression. It only happens in the multi-angle scheme. It does not happen in the single angle scheme where we assume neutrino oscillations are the same for different neutrino trajectories. So that's maybe that will explain this plot. So in this calculation, again, this is our standard calculation in the solid black curve. And then the single angle calculation will start almost immediately. that fast exponential growth you see over here. But is that true? Does the matter suppression explains it? Actually, I have shown a plot earlier. It's not due to matter suppression, because if you dial up or dial down matters, it does not change very much. So in our calculation, the matter density is not that large enough to suppress collective oscillation. So it's not due to the matter effect, then what can it be? It is actually due to the neutrino energy scale itself, or the neutrino forward scattering Hamiltonian itself. So this is that Hamiltonian again. It's proportional to the, see if this one will work better. Okay. So this Hamiltonian is proportional to this neutrino flavor density matrix, and in addition, there's that geometric factor you see. All right, so that geometric factor tells you that there's also a dispersion in this Hamiltonian. For example, if you consider the neutrinos that emitted tangentially from the neutrino sphere, the intersection angle, the average intersection angle with other beams is larger than if it is emitted from along the radial direction. So there's a dispersion in the neutrino Hamiltonian itself. So that's what we call the delta lambda nu. So maybe the criterion for significant collective oscillation is, for that case, is to have the dispersion in vacuum energy scale, that scale comparable to the dispersion in the neutrino Hamiltonian. Actually, we don't really know, because you have to really solve the equation, maybe have some analytical understanding to know. But the reason we proposed this was we did a comparison. We have numerical calculations, and that's the beautiful wedge again in the beginning where the collective oscillations start. So the upper panels show the neutrino survival probability for neutrinos and antineutrinos, and the lower panels showing at the same moment what does the vacuum Hamiltonian plus neutrino Hamiltonian look like. And you see it has the similar wedge pattern. So that's why we propose that that this multi-angle suppression is probably due to the condition that those two dispersions must be comparable. All right. So can that be true? And we of course, we do some numerical exercise. The exercise is, again, the black solid curve is the standard calculation. And then we dial up or dial down the neutrino luminosity. And you see if the neutrino luminosity goes down by, say, factor of 5, the collective oscillation will happen earlier. If you increase the neutrino luminosity by factor of 5, it will happen at much larger radius. And the reason of that is we know the condition, we put the proposed condition for collective oscillation to happen is the dispersion in vacuum scale to be comparable to the dispersion in the neutrino Hamiltonian energy scale. And the dispersion energy in the vacuum scale is fixed. And the dispersion, the lambda dispersion in neutrino Hamiltonian delta lambda nu is proportional to neutrino luminosity over radius to the 4th power. So that condition will tell you how far or how far when you increase neutrino luminosity, the collective oscillation will happen at a later radius. And that actually agree with what we find here pretty well. So that's just some back of the envelope estimates. And we can compare that with the numerical calculations. It looks like it agrees. So that's give us some confidence, but that's not enough, because we see in collective oscillation there's some, not only that the rich pattern, and also in the end there's a stepwise spectral swap or split. So new electron flavored neutrinos swap their energies at particular energy scale, above or below some critical energy scale. That's very interesting, and that's not, of course, you cannot obtain by just this hand-waving argument or simple estimate. So we have to go deeper. So I will mention some of the tools here, and we'll continue in the next lecture. So some of the tools and the toy models, how we can understand that. So let's again come back to the vacuum oscillation I mentioned to you earlier. Why we have neutrino oscillation in the first place was because neutrinos are generalized or detected in the flavor state, electron flavored, mu flavor, and tau flavored neutrinos. And they are not the mass eigenstates. So the mass eigenstates are linear combinations of flavor states. And for two flavor oscillation, you can write down this the Schrodinger equation for vacuum oscillations. This is the flavor wave function, the Hamiltonian, and the flavor wave function. And for this two flavor system, it's just a two component system. And for any two component system, it's equivalent to a spin half particle. We know neutrino is a spin half particle, but what we are not talking about the neutrino, the spin, the actual spin of neutrinos. We're just saying if you have two flavors, it's a two component system. It's equivalent to some spin in some imaginary space. And we can also expand or write the Hamiltonian, a 2x2 Hermitian matrix, or Hamiltonian in terms of the sigma matrix, the Pauli matrices, and identity. So again, this is the standard particle physics model. And what we have here, we are considering this part, the leptons, the neutrinos, and the charged leptons. So in the standard model of particle physics, the charged lepton, for example, electron and neutrinos, electron neutrinos, they are grouped together as a spin space, as what we call weak isospin. It's a weak interaction. So that's SU2 symmetry going into there. Now, if we are considering flavor oscillation, two flavor neutrino oscillations, what we do is we can group the two neutrino flavors together, and we call it neutrino flavor isospin. So it's not the spin of neutrino, but rather a spin vector in an isospace. So JJ mentioned this in the workshop yesterday. So we can define the flavor isospin this way. This is basically the expectation value of this Pauli matrix vector with respect to the neutrino flavor wave function. So for antineutrinos, the spin up in the z-axis means electron flavor neutrino. Spin down means the other flavor sometimes we call mu or tau or x, but really it's represent a linear combination of mu and tau neutrinos. And for maximum mixed, it's represented by a vector in the xy plane. And then for antineutrino, we do something different. If you are a particle physicist, you know what's going on. We have to apply the sigma y transformation here. And so with that in mind, the electron antineutrino is represented by a flavor isospin. It's not the spin of neutrino, it's the flavor isospin in the negative z direction. It's not in the spatial z direction, it's the direction in the flavor space, flavor isospace. And the nu x where nu tau prime is represented by the flavor isospin in the upper direction, and the xy plane give you the maximum mixed neutrinos. And we can also rewrite the Schrodinger equation, and the Hamiltonian, we just write it down in terms of the Pauli matrices, and we get rid of the trace term. Remember, the trace term shift the energy scale, shift the eigenvalues of the Hamiltonian by the same amount. So that just gives you an overall phase for the wave function. It has nothing to do with neutrino oscillation. And then we just write down the equation of motion for this flavor isospin. As JJ mentioned, what we did really was map the SU2 phase, the space for the flavor for the wave function, have the two component system into SO3. And we can write down the equation of motion for flavor isospin, and this H is something like what we call the effective field. It's kind of like if you are familiar with how the classical magnetic dipole spin in the presence of magnetic field, this is how it looks like. So you have a magnetic dipole, and then this is the magnetic field. It will spin around it. Then that's the equation of motion. And of course, we're not talking about the real magnetic field or real spin in this case. It's just an idea. So let me just quickly go through the vacuum oscillation using this picture. So for vacuum oscillation, there's only one term that you remember. The first term in the Hamiltonian represents the vacuum oscillation, and that can be written down as a vacuum oscillation frequency defined as a Maxwell difference over twice neutrino energy, but now I have a plus minus sign. Can you guess what the minus sign is for? Something with the negative energy. Anti-neutrinos, good. So the positive oscillation frequency represent neutrinos, and the negative oscillation frequency represent anti-neutrinos. So we put the both together in a compact scheme. And here is the z-axis. It's not in the spatial space, it's in the flavor isospace. And the Hamiltonian, or the vacuum field, is in this direction. The angle between them is twice the vacuum mixing angle. So if there is no mixing, vacuum mixing angle is 0, then the two directions will be the same. Now suppose we have an electron flavor neutrino produced at time 0. It will be represented by a flavor isospin. How will that flavor isospin look like for electron flavor neutrino? Should it be like this, or should it be like that, or should it be like this, or should it be like that? Should go up, right? It's represented by the flavor isospin in the z direction. That represents electron flavor neutrino. But you see the fields, the magnetic field in this direction. So what it does, just like what the magnetic dipole does in the presence of magnetic field, will just precess around it. All right? So it precesses around it, and then you project its motion in the z-axis. It's oscillating, and that z component of the flavor isospin is actually the neutrino survival probability, although shifted by half. Okay, so that's a very cool picture for you to understand the neutrino oscillation. It's actually a precession in the flavor space. All right, I will stop here and I will continue tomorrow.